All right, it is 10, so let's get started here. So just a couple of notes. Only 2 weeks left of class, so woohoo on that. Test 4 is next week, Wednesday. So just keep that in mind. Our last test before the final will be next week, Wednesday. And I'll talk more about the final when we get closer to it, but it will be cumulative, just so you know. So let's actually get into what we're going to be talking about today then. And we're going to look at Lewis structures and the Lewis model of bonding to understand why do some molecules form a covalent bond? Why do some molecules form an ionic bond? And this has to do with valence electrons. And let's just remember our terminology here. You have two types of electrons. You have core electrons and you have valence electrons. Valence electrons are the outer shell. It's your highest energy level. And the Lewis model really says it's these valence electrons that are really doing all of our chemistry, right? That's what we really care about. And so to understand how Lewis models work, the first thing we're going to do is learn how to create Lewis structures, also called electron dot structures, right? And that's what's being shown up here. Here I have a molecule that is created using Lewis dots. And just so you know, every single dot is an electron, a valence electron, right? So every single dot here is showing a valence electron. When you have two dots between two molecules, that's a covalent bond. Usually we just show them as a straight line, but in the Lewis dot model, we have two electrons forming a single bond because they're sharing an electron. 4 dots is a double bond, which is shown like that normally with 2 lines. So that means 2 atoms are sharing 4 electrons. And then a triple bond is 6 electrons, which in the line notation would be like that, which means these 2 atoms are sharing 6 electrons. And once we learn how to do the Lewis model structures, that really unlocks a lot of things, lots of things about understanding molecules. So we'll understand their size, what shape they take, whether they're polar or not. And polarity means imbalance of electrons. What I mean by that is like electrons gather at one part of the molecule versus another. That means one part of the molecule would be more negative and another part would be more positive. And we can also look at stability in terms of bonds, which bonds are more stable than others. And that all comes from really understanding how the Lewis model works. And the first thing we're going to do is learn how to do Lewis structures. So I'm going to do A. So draw the Lewis symbol or structure. So if you see Lewis symbol, I'm most likely going to call it structure, although I might call it symbol. They mean the same thing here. So draw the Lewis symbol for nitrogen. All right. So to show you how to do this, I'm going to do the electron configuration for nitrogen. Well, I guess it is write the electron configuration and Lewis symbol. So I have to do both. Okay, so let's write the electron configuration for nitrogen, and that would be helium, 2s2, 2p3. Hopefully everybody's comfortable with electron configurations at this point. And that's our electron configuration. Well, yeah, so you could do 1s2 instead of helium if you wanted to. It doesn't matter. Remember, our noble gas can be shorthand. So let's do a Lewis symbol. So to write a Lewis symbol, what you do is you just write the element's atomic symbol, so nitrogen. And what you want to imagine is that there are 4 boxes around nitrogen. Now in the Lewis symbol, we're not actually going to write these boxes. I'm just doing for demonstration purposes. And the way I think about these boxes is that one box is the s orbital, one box is and the 3 remaining boxes are the p orbitals. Now, as we learn more about Lewis symbols, this actually gets a little more complicated because I'm not including d orbitals here, but let's just start simple. So let's imagine we're working with elements that do not have d orbitals right now. And so around that element, I have a place to put the s orbital electrons and a place to put the p orbital electrons. So if I look at my electron configuration, I have 2 s orbital electrons. So I put 2 electrons there. And I have 3 p orbital electrons. And if you remember, one of our rules is that don't pair up electrons unless you have to. So since I have 3 p orbitals, I'm going to put them each in a different box for the p orbital. It's like how we were doing the dashes, right? So if I was doing the dash system, well, I don't know why I made those dashes so big. So that's a p orbital, p orbital, p orbital, 2, 2, 2, and we are 2 at p3. So if I was doing the dash system, it would look like that, right? My electrons would want to be by themselves. I'm doing the same thing with my Lewis symbol. And so the way to write nitrogen as a Lewis symbol would be this, based on what I showed there. So we have 5 valence electrons surrounding our nitrogen. We got those valence electrons from our electron configurations. So questions about the Lewis symbol there? All right, try to practice yourself with B, C, D, and E. How do you know you have 3 p orbitals and 1 s? Remember, that comes from our L's and M's of L's, right? So of an S, L is 0, M's of L is 0, right? So I only have 1 dash. For P, that's when L is 1. So we have 3 M's of L values. M's of L is -1, 0, or +1. So I have 3 dashes. Because our M's of L rules are -L, 2L, including 0. So that's how I know how many dashes. All right, so let's try and do these other orbitals, other Lewis symbols. And it doesn't matter if I want to put the s orbital on the bottom of the N or left or right. Generally, no, it doesn't matter. We'll do about 1 more minute. Yeah, then I'll come back with the answers. All right, so let's take a look at these. So start with the aluminum here. The electron configuration of aluminum is neon. 3s2. Whoops, 3s2, 3p1. So we should have 3 valence electrons. So aluminum looks something like that. Or you have your s orbitals together, and then your p electron right there. Rather, your s electrons together, and then your p electron all by itself. You can also, people will also write aluminum like this, by the way. It's not wrong per se. I just think the one on the left is more correct. All right, sodium plus. So remember, plus means we lose an electron. So what I'm going to do for the first time we do one of these, I'm just going to write sodium. I'm going to give you the electron configuration of sodium and then go to sodium plus. And for this, since we're dealing with an ion, I'm going to write the whole thing out. So it is 1s2, 2s2, 2p6, 3s1. And for sodium plus, we lose an electron, so it's 1s2, 2s2, 2p6. Right. So that's the difference there. And what's tricky about ions is that, well, let me just do sodium. So sodium would look like this. And sodium plus And you do have to write the charge symbol at the top. So the Lewis symbol, you have to say the charge in the top corner. So the difference between sodium and sodium plus is that you lose one electron. And that's actually how you write sodium plus. There's nothing around it, right? You don't add the 8 electrons, even though they are valence now. You write ions using their neutral Lewis structure as your template. So what I mean by that is I find it easier when learning this, write out the neutral molecule. And then if you're removing electrons, remove from your neutral molecule, and that's what you're left with. If you're adding electrons, add it to your neutral molecule. So that is sodium plus. So sulfur 2 minus, the electron configuration of sulfur 2 minus, which is right here, would be neon 3s2 3p6. So sulfur, and then you have to write the charge in the top there. Usually you want to put it around brackets. And it has 8 valence electrons. So we write 8 dots like that. That's a Lewis symbol for sulfur 2 minus. Magnesium 2 plus, it's going to be the same at how we did sodium. So magnesium, so again, just for teaching purposes, I'm going to write magnesium and then the ion electron configuration. You don't have to do this. I just like to do it to show it. So magnesium is neon 3s2. And magnesium 2 plus, we lose those, so it's just neon. So when doing the Lewis symbols, magnesium would be like this. And for the 2 plus, I'm losing 2 electrons, so I lose those 2 dots. So magnesium 2 plus looks like this now. And so those are our Lewis symbols. And using that information, we can pretty much write a Lewis symbol for any element on the periodic table. All right, questions on how to write Lewis symbols or Lewis structures? All right. So the next topic we're going to talk about is all about bonding, right? So we're going to review the type of bonds we have between molecules, between atoms, and then tie that together with our Lewis structure. So let's go with the ionic bonds. And if you remember, an ionic bond is the bond between a metal and a nonmetal. And we've learned already this semester, what will happen is that a metal will lose an electron in between and become a cation. And we now know the reason why they do that. It's because metals have these low ionization energies, because when they lose electrons, they can have the electron configuration of noble gases. So this ties together what we've been talking about the last week or so. In nonmetals, they want to gain electrons because they have high electron affinities, and they become an anion. And when they gain an electron, they can now have the electron configuration of a noble gas, and they're stable. And so what happens is that the metal will give an electron to the nonmetal, or multiple electrons. It doesn't just have to be one. And when that happens, the metal is positively charged, the nonmetal is negatively charged. They stick together, right? So an ionic bond is really just like mini magnets sticking together. They're not sharing electrons. Rather, the metal gives an electron away, the nonmetal accepts it, and now they're attracted to each other. And ionic bonds are really strong. It's really hard to break an ionic bond unless you're in like water. Water is very good at breaking those. But like salt, if you try to like break apart ionic bonds of salt and make it a liquid, that takes a lot of heat to make salt a liquid. It's possible, and people study that, but it takes a lot of energy to do that. And compare that with our covalent bond, which is nonmetals plus a nonmetal. Oops. And covalent bonds are sharing of electrons, like we talked about, right? And here we have CH4. You can see in our Lewis structure, we have 2 electrons being shared between each carbon and hydrogen. And since they share electrons, this is a way for nonmetals to have their full octet. That is, to have their 8 valence electrons and be the electron configuration of the noble gas. Because if you look, we have carbon with 4 electrons. And I know I'm drawing carbon different than what I just told you a couple minutes ago about the s&p orbitals, but I'm doing this because I'm going to bond it. So carbon has 4 electrons, 4 valence electrons, and it wants to get to 8. Hydrogen has 1 valence electron, and hydrogen wants to get to 2. So hydrogen's the oddball, in that it always wants to get 2 electrons, not 8. Well, hydrogen and carbon are both nonmetals, so they have to share with each other. And so if one hydrogen comes along, they can share that electron. And then another hydrogen can share its electron. Another hydrogen can share its electron. And another hydrogen can share its electron. And since they're sharing, as shown in this model here, carbon can feel all 8 electrons. So carbon feels like it has a full octet now, right? Because it has 8 electrons around it. Each hydrogen now feels like it has 2 electrons around it, so they're happy. And that's why we have covalent bonds. These atoms are trying to get to their octets, and they do that through sharing. And the way they share it is directly between each other, as shown in these images. Remember that nuclei of atoms are positive, electrons are negative. So the most stable way to share electrons is by putting them right between the nuclei. So they're equal distance from each positive nucleus. And also the nuclei aren't interacting with each other. If you look at this image on the left, the electrons are equal distance from each nucleus, but now the nucleuses can like feel each other and they would want to repel. Here, they are being screened by this negative electron. They don't see each other as being positive because they're too busy focusing on that electric charge right in the middle. So that's the covalent bond. And the last type of bond is the metallic bond. And that's when you have metal atoms interacting with each other. So this is metal atoms only. And as we've learned, metal ions or metal atoms have low ionization energies. It's really easy for metals to lose electrons. So what happens if you have a bunch of metals bound together, like in this piece of copper, they just release all their valence electrons, and it's like all the metal ions are just in a wave of electrons. They're sharing their electrons with everybody. It's a giant pool, right? They're just swimming in a sea of electrons. So that's different than the ionic bond, which you just give an electron to one person or one atom, and that other atom takes it. A covalent bond is you're sharing electrons between 2 atoms. The metal bond is you release them to the world, everyone shares, right? So those are the three different types of bonds. And each type of molecule, depending on who you're pairing with, you're going to prefer one type of bond or another. So before we move on, are there any questions about the types of bonds in chemistry? Right. So what we're going to do is we're going to start by learning how to draw Lewis symbols for ionic compounds. So let's start with NaF, right? So Na, again, for teaching purposes, I'm going to draw the neutral forms first. You don't have to do this. I'm just looking for the ionic form in the actual answer. But for teaching purposes, here's neutral sodium and here's neutral fluorine. Sodium's a metal, fluorine's a non-metal. So when a metal and a non-metal interacts, the metal gives the electron to the non-metal. And so for sodium fluoride, I guess that's brackets. Our Lewis symbol would be sodium positively charged with nothing around it. And fluorine negatively charged with 8 electrons around it. Right? And so that's your goal for B, C, D, and E. Right? The Lewis symbols for these ions in the ionic compound. So take a stab at that and let me know if you have questions. how do the numbers affect things? So like Br2 means you have 2 atoms of bromine you have to work with. Right, so each bromine needs to have 8 electrons. Let me actually do an example of that. So I'll go ahead and do C then. So in case you're not sure about that. So we have SR, BR2. Neutral SR is in the second column, so it has 2 valence electrons. Br is a halogen. We have 2. So each of those have 7. Right, so SR is going to give 1 electron to this Br to make that a full octet. Then it's going to give the other electron to this Br. So now SR has lost all of its electrons, valence electrons, so it's happy. And it lost 2, so it's SR2 plus. And then we have Br minus, and another Br minus. So that's how I write it out. Being more correct, I should have ordered them as Br, SR, Br, but it really doesn't matter for this part of the demonstration. But yeah, that's how you handle multiple ions. So we'll do like 2 to 3 more minutes on this. All right. So let's do calcium oxide. Calcium has 2 valence electrons. Oxygen has 6. 1 electron here, 1 electron here. Calcium, 2 plus. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 2 minus because it gained 2 electrons. Then potassium oxide. So we have 2 potassiums, each one with 1 electron, 1 valence electron. Again, oxygen has 6. Give 1 to you. Give 1 to you. So we have calcium plus. Now I'm going to put my oxygen in the middle. 1, 2, 3, 4, 5, 6, 7, 8, because it got 2 electrons. And since it got 2 electrons, it's 2 minus. And on the other side is another calcium plus. Or potassium, not calcium, potassium. Then we have lithium sulfide. So it's the same idea as in D, where we have 2 lithiums, each with 1 electron. Sulfur has 6 electrons. And so 1 here, 1 here. So lithium plus sulfur, 2 minus, then lithium plus. And that's our Lewis symbols for ionic compounds. And so now we can actually understand why things become +1, +2, -1, -2. It all has to do with wanting that full octet. All right. So any questions about this idea? All right, let's move on then. So here's something a little more advanced then. Here I'm just giving you two elements. I'm asking you to say, okay, when these elements combined, what is going to be their formula? So to show what I mean, let's do Na and S. So we have sodium, which has 1 valence electron, and sulfur, which has 6. All right. So the goals of metals want to lose all their valence electrons, right? The goals of nonmetals, they want 8 valence electrons. So metals lose valence electrons. Nonmetals want to have 8 valence electrons. So let's begin with that. So sodium would give its electron to sulfur. And I'm just going to show the progression here as a teaching exercise again. So when I do that, sodium lost all its electrons and is +1. It's happy. It's good to go. Sulfur has 7 valence electrons and it's a -1 charge now because it gained an electron. But sulfur's sad. That's a frowning face, by the way. Sulfur's sad because it wants 8 valence electrons. So how are we going to fix that? Well, we can only add sodium. We can add more sodium to make this happen, and only sodium because that's what the question is saying. So I can add another sodium ion or atom here, which has 1 valence electron. Give that to sulfur. And when we have that, I have 2 sodiums that lost their electrons. So they're happy. I also have a sulfur that has a full octet and it's -2, so it's happy. So when sodium and sulfur combine, they will always make Na2S because it takes 2 sodiums to give sulfur a full octet, right? Because sodium only gives 1 electron at a time, and sulfur needs 2 electrons to get that full octet. So we need 2 sodiums. So that's the gist here. Try to use our Lewis symbols to figure out when we're combining those compounds, what will be the formula, right? So if you have questions, let me know. Otherwise, I'm going to give you a few minutes to try this out. Right, so let's take a look at this. So calcium and nitrogen. So let's start with our Lewis symbol for one each. I'm going to do it down here to give myself some space. Calcium, 2 valence electrons. Nitrogen has 5. 2, 3, 4, 5. So I give a valence electron here. So calcium gives 1 away. And calcium gives the other 1 away. So calcium becomes 2 plus, and it's happy, lost all its electrons. Nitrogen is now at 7. So it is now 2 minus. But it's not happy because it only has 7. And it needs 8. So let's add another calcium. And calcium gives 1 electron away to nitrogen. And after that, we have calcium 2 plus. So that calcium's happy. Calcium 1 plus, not happy because it still has 1 electron. And nitrogen has a full octet as 3 minus. So that nitrogen's happy. So we're good there. But that calcium on the bottom still has 1 electron remaining we need to get rid of. So let's bring another nitrogen in. So I give that away, give that valence electron away. Makes this calcium 2 plus. That calcium's good to go. However, so I have calcium 2 plus, calcium 2 plus, nitrogen full octet, minus 3. And then this nitrogen currently has only 6, so it needs 2 more. Well, how convenient that calcium has 2 electrons. Give 1 here, give 1 here. Now everyone is satisfied, right? Every metal ion has lost all valence electrons. Every non-metal ion has a full octet. So the molecular formula for when calcium and nitrogen interacts is Ca3N2, right? For this to be a neutral compound, you need 3 calciums. Let me write that 3 a little better. You need 3 calciums and 2 nitrogens. So before I move on to CSF, which is way easier than B, any questions about B? All right, so C, cesium, 1 valence electron, fluorine, 7. So that's easy. I just give that there. CS has no valence electrons, fluorine has 8. So this is just a 1-to-1 ratio, CSF. And that is how we can use Lewis symbols and the idea of full octets to determine when a metal and a non-metal interact. We can usually determine in what combination they'll interact. What is their molecular formula? I have a question somewhat related to this. On the periodic table, how do the groups in the middle, RUH, have 5s1 plus some Ds? So what's happening there is more complicated than what we're going to cover in general chemistry. But those energy levels are so close to each other. Like if you look at the energy difference between 5s and a 4d, it's not all that different. So it is lower in energy for an electron not to be paired and to be in the d orbital than to be paired up in the s orbital. So when we look at some elements in the d shells, yes, a lot of times it will be in S1. and that has to do with the energy of pairing. Electrons don't want to be paired, so if you have another shell that's close, you'll just go in there. That's why you'll see some elements like on your periodic table, if you have all those written down, like some periodic tables have those. That's why you'll see that. On a test, since we haven't explicitly covered that topic, and it's a topic that you can't tell by looking at the element. You have to do an experiment on that. So we're always going to assume for our purposes, the s orbital gets filled up first. But yep, that's why. But yeah, any other questions here? Right. So this is a good place to stop as we're out of time anyways. So on Wednesday, we're gonna just do a couple more questions. Should be rather quick to get through, talking about lattice energies. And then we'll continue our look into Lewis simples on Wednesday. I'll put a homework up here for people to practice more on their own. And yeah, otherwise, hope you have a good week. Hope to see you on Wednesday, and have a good one, everybody.